Hello, math friends. Welcome to AP Calculus, Derivatives of Inverse Functions. This is our final section in Chapter 3, and this content is actually not provided for us in our textbook. However, it is on the AP exam, so I felt it was important to include it in the Chapter 3 content when we start talking about derivatives. Today, we're going to be talking about the derivatives of inverse functions. Now, we have certainly talked about inverse functions many times before in different math courses, so you know what an inverse function is. If you have a given function f of x, then its inverse function, and again, inverse is noted with that looks like a little -1 exponent, so f to the -1 power of x is what it looks like, but we don't say -1 power, we say f inverse. So the inverse function, f inverse of x, is defined to be the function whose domain is the range of f of x and whose range is the domain of f of x. So as we already know from our previous experience, a function and its inverse, their domain and their range, exchange places. If f of 3 is 5 on f of x, then f inverse of 5 would be 3 on f inverse of x. And then we have two different representations of inverses. Here we have a graphical representation in which we know that a function and its inverse will always be reflections of each other over that diagonal line y equals x in the coordinate plane. And you should remember from Algebra 2 the analytical representation of an inverse function. If I said we have two functions, f of x and g of x, prove that they are inverses. Remember, we used to do the two compositions, f of g of x and g of f of x. And if those two functions were actually inverses of each other, the compositions would always give us back the same thing, and that special thing that we would get would always be x. So here, our analytical representation of an inverse would be if f inverse of x is the inverse of f of x, then the composition f of f inverse of x is equal to x, and f inverse of f of x is equal to x. So that's the idea of f of x and g of x being a function and its inverse. We're just not calling the inverse g of x, we're calling it f inverse of x. Let's take a look at example 1. We are provided a small table here where we have two functions, f of x and g of x. We have two values of x that are given, x equals -2 and x equals +1, and then we have the values, the corresponding y values on our f of x function and our g of x function. And we are asked to complete the table of values. So in the first table, we are given that x is 3, and we want to know what is f inverse of x. Again, we don't have f inverse in our table, but we do have f. So when x is 3, that would give us some value of f of x, or excuse me, when x is -2, that gives us the value 3 for f of x. Then if x is 3, we should be able to determine that f inverse of x is going to be the x value, which is -2, right? So we're looking at this relationship right here, and we are basically flip-flopping our domain and our range. And the second example is the same way. We know that when x is 1, f of x is 2. So now they're saying, well, if x is 2, what is f inverse of x? Well, the answer is that has to be a value of 1. All right, let's do the same thing with our g of x. If we know that when x is 1, g of x is -2, so then we want to know, well, what is g inverse of x when x is 1? So right here, we can determine that that has to be the value -2. And then finally, when x is 1, g of x is -2, so if x is -2, then g of x has to be a value of 1. So again, just looking at flip-flopping our domain and our range here. Letter B gives us 4 different situations, and again, we are using the same table of values above to answer the following questions. The first one is f of g inverse of -2. So we should start on the inside and we should work our way out. So we begin with, what is g inverse of -2? And g inverse of -2, again, if we look at our table, we know that g inverse of -2 is 1, because when x is 1, g of x is -2. So g inverse of -2 should give us an output of 1. And then that means we are trying to find f of 1. And again, from our table, when x is 1, f of 1 gives us a value of 2. So that means that f of g inverse of -2 is 2. The second one, f inverse of f of 1. So again, we start right here on the inside with f of 1, and f of 1 is 2. Then we have to do f inverse of 2 and figure out what that is. Well, we know that when f of x is 2, x is 1. So f inverse of 2 is 1. The next example, we are asked to find g inverse of f inverse of 2. So again, start on the inside. So begin with f inverse of 2. And f inverse of 2 has to be 1, because when x is 1, f of x is 2. And then g inverse of 1, again, looking at our table, well, g of x is 1 when x is -2. So g inverse of 1 is -2. So our answer, g inverse of f inverse of 2, is going to be equal to -2. And then the last one, we've got a composition of 3 functions here. So start on the very inside, start with g inverse of 1. And when g of x is 1, x is -2, right? So this is going to be -2. So then the next thing would be g of that. So g of -2 is 1 from the table. And then finally, f inverse of 1. Oh, I don't have that value because there is no f of x value of 1, so I can't work backwards. So I have to say that based on the table of information that I'm given, this value is undefined. So f inverse of g inverse of 1 is undefined. The relationship that exists when a composite function is formed using a function and its inverse is that f of f inverse of x equals x. That's what we were talking about earlier when we talked about, back in Algebra 2, show that f of g of x equals x, show that g of f of x equals x. We just called g of x f inverse of x. So f of f inverse of x, that composition has to equal x. Well, we can actually use the chain rule, and we can differentiate both sides of this equation to find a formula for the derivative of the inverse function f inverse x. So I will start by just showing that I am taking the derivative of both sides of the equation using Leibniz notation. And we're going to be getting into this shortly. We're going to be using more Leibniz notation and showing the derivative of both sides of an equal sign. So my first step is just going to be d dx. That just means the derivative with respect to x of f inverse of x is equal to the derivative with respect to x of x. And now I take the derivative of the left side of the equal sign, and I take the derivative of the right side of the equal sign. Well, on the left side, I have a composition, so I know that this is going to be chain rule. So I know I'm going to have the derivative of the outer. The outer function is f, so it's going to be f prime of, and then at the inner, so f prime of f inverse of x, times the derivative of the inner. Well, how do we write the derivative of f inverse of x? We put the f inverse of x in a bracket, and then we put the little derivative tick mark thing after it. Okay, so this is the derivative of the outer at the inner times the derivative of the inner. And we know that this is equal to the derivative of x, which is 1. And so if we want an expression for the derivative of the inverse function, that's this, right? That's f inverse of x prime. Well, that's going to be equal to 1 over, and then I just have to divide by the derivative of the outer at the inner from the left side of the equal sign. So f prime of f inverse of x. So here is our definition of the derivative of the inverse function that we just found using the chain rule. In example 2, it says, suppose that f of x is equal to 3x plus 2, and f prime of negative 2 equals 3. What is the value of f inverse of negative 4, the derivative of that, right? F inverse of negative 4 prime, which is the derivative of f inverse at x equals 4. So the first thing is, if we want the derivative of f inverse at negative 4, then we need to know where f of x is equal to negative 4. So let's write that down. If we want f inverse of negative 4 prime, we need to know where f of x equals negative 4. So we do that ordered pair. Well, we have an expression for f of x. So 3x plus 2, we want to know when that equals negative 4. So let's solve for x. We subtract 2 from both sides. We get 3x is equal to negative 6. Divide by 3, and we get x equals negative 2. So we just found out an important relationship that we need, and that is that f of negative 2 is negative 4, and that means that f inverse of negative 4 would be negative 2 because of the relationship of a function and its inverse, its domain and its range flip-flop. So these are two important ordered pairs that we need because we want to find f inverse of x prime, and we know that that's equal to, this is just from the previous problem, f prime of f inverse of x. So for this particular problem, we know x is negative 4, so we want to find f inverse of negative 4 prime, or the derivative of f inverse at negative 4. So this is going to be equal to 1 over f prime of f inverse of negative 4. Well, I know f inverse of negative 4 is negative 2. So this becomes f prime of negative 2 in the bottom, and I was given f prime of negative 2 equals 3. up here in the original problem, right? So 1 over 3. So my answer here is that f inverse of negative 4 prime is equal to 1/3. Our final example has many parts, and all of the parts use this given table of values. Parts A and B are very straightforward. These are just inverse derivative calculations. Part A wants us to find the value of f inverse of 3. So again, I'm just going to write down my equation for the derivative of f inverse. We've used it quite a few times already now after deriving it using the chain rule. So f inverse prime is equal to 1 over f prime of f inverse of x. Okay, so that's the formula that we're using. So for example A, the derivative of f inverse at x equals 3 is going to be equal to 1 over f prime of f inverse of 3. And I can use the table to figure out this information. So f inverse of 3 means, do I have a value for f of x being 3? I do. And the x value that gave us that was 1. So if when x is 1, f of x is 3. If f inverse is 3, then x is 1, right? That's that relationship. So this bottom becomes 1 over f prime of 1. And then f prime of 1, when x is 1, f prime of 1 is 2. So this slope is, or this value, I should say, excuse me, is 1/2. It is a slope because it's a derivative. Find the value of g inverse of negative 2. Same routine that I just went through. So I'm going to begin here with g inverse of negative 2 prime is equal to 1 over g prime of g inverse of negative 2. And then I'm going to look in my table to get this value right here. So g inverse of negative 2 gives me an output of 1 from my table right here. That's where I'm looking. So this is 1 over g prime of 1. And then g prime of 1, well, when x is 1, g prime of 1 is 1. So I'm left with 1 over 1, which I know is a value or a slope of 1. Part C says, find the value of g inverse of 1 prime. Then find the equation of the tangent line to the graph of g inverse when x is 1. So first, let's do what we've been doing. Let's find our slope, because our slope is our derivative of g inverse at x equals 1. So g inverse of 1 prime is going to be equal to 1 over g prime of g inverse of 1. And again, using my table, g inverse of 1 has a value of 3. So this becomes 1 over g prime of 3. And then when x is 3, g prime is negative 2. So right there, I know that my slope of my tangent line is going to be negative 1/2. Okay, then the next thing is I need to find my point. Well, I know that It's when x is 1. So what is the value of g inverse when x is 1? The value is 3. So that means that 1, 3, this is my point of tangency. So now obviously my last step is just point slope form. So y minus 3 equals negative 1/2 times x minus 1. And when we solve this for y, we get y equals negative 1/2 x. Negative 1/2 of negative 1 is positive 1/2. You add the 3 and you get a y-intercept of 3.5. So there is the equation of the tangent line. Part D asks us to estimate the value of g prime of negative 1. Notice that we don't have any x values of negative 1 in our table, so we don't have a value for g prime when x is negative 1. Based on this value, what conclusion can be reached about the graph of g when x is negative 1? Well, again, here's the key word in this problem. It says to estimate, right? Since we don't have an x value of negative 1 in our table, the best thing that we can do is to calculate a slope using 2 points where x is close to negative 1. So how about if we do when x is negative 2 and when x is 0? Those are the two closest x values, and we can use those two x values to calculate a slope and assume that that's a good estimate for the slope when x is negative 1. So I will say that g prime, and actually let's first write that down, that we only have a table of values. Okay, so we have to estimate values of g prime of x, which are our slopes, using points from g of x. Okay, so let's do that. G prime of negative 1, we're going to say is approximately equal to the slope that we get when we do g of negative 2 minus g of 0 divided by negative 2 minus 0. Again, because we don't have an x value of negative 1 in our table, we're going to use the x values negative 2 and 0. Those are surrounding negative 1. Well, from the table, g of negative 2 is 2, and g of 0 is negative 3. 2 minus negative 3 is positive 5, so we end up with negative 5/2 for our answer, which is our slope of g at negative 1, or the value of g prime of negative 1. And they ask us to give some sort of a conclusion that can be reached about the graph of g when x is negative 1. Well, when x is negative 1, we found that the graph has a negative slope. So what conclusion can we make? Think about the relationships between the slopes on the derivative function and how that relates back to the antiderivative or the original function. So we can say, since g prime of negative 1 is less than 0, then the graph of g is decreasing, right? If the slope is negative, the graph has to be going down. So we can say the graph of g is decreasing. Our final question, part E, asks us to do the same thing as we did in the previous problem. Estimate the value of g prime prime of negative 1. Well, we know that g prime prime is the derivative of g prime. So again, a derivative is still a slope, but this time we're finding slopes from points on g prime instead of on g. So once again, I'm going to make a little note. We only have a table of values. So we have to estimate values of g prime prime of x, which are our slopes, using points from g prime of x. So we will say that g prime prime of -1 is going to be approximately equal to, and again, if we're looking at -1, we're going to use x equals -2 and x equals 0. Those are the closest x values we have to -1. So g prime of -2 minus g prime of 0 divided by -2 minus 0. And from our table, g prime of -2 is 3. And g prime of 0 is 2. -2 minus 0 is -2. So we end up with an answer of -1/2. And once again, very similar conclusion. Since g prime prime of -1 was less than 0, we can assume that the graph of g prime is decreasing because the slope is negative.